Okay, in this podcast we're going to talk about electronegativity. So if we think about a bond, we will often draw it like this, and here's two electrons being shared between a hydrogen. So if I look at those electrons, they're going to be shared pretty much in between the two. But if I take the same single bond between a hydrogen and a chlorine, I have two electrons. In fact, the hydrogen does not attract the electrons as closely to it as the chlorine does. And if you could draw the electron cloud, you would see a greater density of electrons in that bond closer to the chlorine than you would to the hydrogen. Okay, and as opposed to the hydrogen-hydrogen bond where the cloud is pretty much symmetrical. It's pretty much in the middle, which means that they share electrons equally. This is electrons not being shared equally, and one side of that bond ends up, call it a sigma negative, a slightly more negative side, and this is a slightly more positive side. So electronegativity is simply the tendency of an atom to attract electrons to itself in a covalent bond. Or it's a tendency to be an electron hog. So the more an element wants to attract electrons, the higher the electronegativity, right? The more it wants to hog the electrons. Okay. So let's think about which elements are most likely to hog electrons. So here, if I look at group 1, they have one valence electron. Are they trying to gain electrons? No, they are not. So they're going to be low in electronegativity. If I think about fluorine, chlorine, and bromine, they have 7. 1, 2, 3, 4, 5, 6, 7. Not quite on the line, but they have 7 valence electrons. They want another electron very much so. So they are going to be high in electronegativity. Now let's talk about the noble gases. Of course they have 8. They have a full valence shell, so they have really no electronegativity and often are not even listed in the table. Okay, so the high is going to be this group here, the halogens. Okay, so let's think about what happens as we go down a group. We go from period to period. Okay. What happens is, again, if I have this nucleus, every time I add a shell with electrons in it, the Coulombic forces are weaker for these electrons that are further away. And if they're further away from that positive pull, and it's really, when I have a bond, let's say between hydrogen and hydrogen, it's not the attraction the electrons have for each other, it's the attraction that the negative electron has for the positive nucleus of the other, right? That's the Coulombic attraction. It's the nucleus of one being attracted to the negative of the other, okay? So if this electron out here, this negative electron, is further away from the positive nucleus of an adjacent atom, it's going to have less pull from that nucleus. Okay, so as I go down, so electronegativity will decrease. Okay, so across a period, electronegativity goes up, and down a group, electronegativity goes down. Now, in fact, Linus Pauling came up with this idea of electronegativity, and there's something called the Pauling scale. And the electronegativity is not like energy. There are no units associated with it. It is an arbitrary scale, and the element that has the highest electronegativity was assigned to the value of 4. And everything else is compared to it. So pause me for a minute and think about which element you think is going to be the highest in electronegativity. And after you think about it for a second, come on back. Okay, welcome back. Well, if you guessed that it was fluorine, then you are right. These are going to have very low noble gases, right? So it's going to be furthest to the right and the one with the fewest shells. So it's going to be fluorine that has the highest electronegativity, and its value is 4. and you can get a periodic table that lists the electronegativities on it, and all of the electronegativities are compared to the strength of pulling electrons toward it of fluorine. Okay. And here's the trend. Here we have atomic number, and then this is the Pauling scale of electronegativities. You can see the high is 4 there, and that is going to be fluorine. So as you go across a row, across a period, electronegativity goes up. As you go down a group, it goes down slightly. Much bigger change from the number of valence electrons. Okay? Alright. So let's take a look at trends overall. So I like to think about anchoring myself up here in the right hand corner. And here's where I have the highest electronegativity. I have the highest ionization energy. And I have because of the strong Coulombic attractions, I also have the smallest atomic radius. Okay, so these are large, these two. Whoops, let's just go back. These are large, and the radius is small. Okay, and then of course it'll go down from here. The other property sometimes we talk about is metallic character, and metallic character, of course the elements are organized, so the metals are here, so of course it's going to be closer to this side, it's going to be higher metallic, right? Higher metallic on the left side of the periodic table, but it's really a measure very much like ionization energy. Those metals that are most likely to give up electrons are going to be those down here. So again, the high on metallic character is going to be towards the lower left of the periodic table. Okay, so we're going to stop there.